Okay, now let's learn about the p-value method for hypothesis testing. So I'll just go straight to an example here, and I'll test the hypotheses that are in this problem using the p-value method. A large company thinks the average salary of all its employees is less than $60,000. They select a sample of 30 employees. Their average is 59,100. Population standard deviation is 1,500. Alpha's 0.01, that's 1%. Does the company appear to be correct? Okay, well, the company thinks the average salary for all its employees is less than 60,000. So population mean, less than 60,000. That's the alternative hypothesis. I know it's the alternative because of the less than sign. The null hypothesis would be that the average is actually equal to 60,000. Okay, now if we want to put those hypotheses to the test, we learned the traditional method last time, but I'm going to show you another method today called the p-value method. And there's a lot of overlap and similarities between the two methods, but there is a slight difference. Okay, we still have to conduct an experiment or do some research, which was done here where 30 people were selected. That's the sample size. The sample average was 59,100, and we still need to know the population standard deviation, which is 1,500. Now, just as we saw before, we can't jump to a quick conclusion. We have to analyze things a little further. We're going to say with a sample size of 30 that the sample mean has a normal distribution. So there's the bell-shaped curve. We're going to assume that the null hypothesis is true. So we'll assume that 60,000 is in the center of the bell shape. And now the sample average we got is 59,100. What we do in the p-value method is rather than get some critical value and see where that value falls in relation to the critical value, what we do is we mark down the sample average, and then if we're doing a left tail test, we'll shade to the left. We're doing a left tail test here because of the less than sign in the alternative hypothesis. So we'll shade to the left, and then the p-value, which stands for probability value, is the amount of area that we've shaded. Well, in order to find that area, we're going to have to convert our sample average into a z-score and then go to our standard normal chart. So you remember our z-score calculation, sample average, which is 59,100, minus what we're assuming to be true for the population mean, which is 60,000, divided by standard deviation 1,500 over the square root of the sample size, which is 30. Okay, you can do the calculation. We've done that many times, so you should be comfortable with that calculation by now. It's negative 3.29. So the p-value is the area to the left of the z-score, negative 3.29, in a standard normal distribution. So you can go to your standard normal chart. You can go to negative 3.29, and you get the area 0.0005. So the p-value is 0.0005. That basically represents the probability that you would get a sample mean that is at least this far away from what you assume to be true about the population mean. Well, the way we come to our conclusion with the p-value method is we compare that p-value to the alpha value. In this case, the p-value is less than or equal to the alpha value. Whenever the p-value is less than or equal to the alpha value, so 0.005 is less than 0.0100, the conclusion is to reject the null hypothesis. Okay, the reason why is that alpha value, that level of significance, represents the maximum probability that we're willing to take in rejecting the null hypothesis by mistake. The p-value is, in a sense, it's the probability that you would be rejecting the null hypothesis by mistake if you got this kind of sample average from a distribution that's centered wherever you assumed it to be. So if the p-value is smaller than the alpha value, that means the actual risk is less than your risk tolerance, then you can go ahead and reject the null hypothesis and feel comfortable with that. If the p-value were greater than the alpha value, that would indicate that it's too risky to reject the null hypothesis, and so you would come to that conclusion. Okay, let's just do two more examples here just to give you some extra practice. A college says the average class size of all its classes is 24.0. You think it's higher. You look at a sample of 36 classes, their average size is 24.7. Population standard deviation is 2. we'll use alpha equal to 1% here, can we say that the hypothesis looks correct? Well, the college that says that the average is greater than 24, that's the alternative. Therefore, the null would be that the average is equal to 24. Remember, the null always has equals, and the numbers are going to be the same in the two hypotheses. As far as the experiment and the research go, we studied a sample of 36, and we got a sample average of 24.7, and we found out the population standard deviation is 2. Well, the sample size has 30 or more, so we can say that the sample average has a normal distribution. If we assume the null hypothesis is true, then we assume 24 is in the center of that distribution. We mark our sample average, which is 24.7, and we're doing a right tail test here because of the greater than sign in the alternative hypothesis, so we shade to the right. Now the p-value is the amount of area that we've shaded here in the right tail. In order to get the amount of area that we've shaded, we have to convert everything to z-scores. So remember, in terms of z-scores, the mean in the center of the distribution would be 0. To convert the 24.7, we take that value minus what we assume to be the population mean, which is 24, divided by the standard deviation 2 over the square root of the sample size, so over the square root of 36. That gives us 2.10. So we're looking for the area to the right of 2.10 in a standard normal distribution. Now, I'm not going to keep flipping back between the chart because we've seen that enough times. You should be okay with doing that. But if you look up 2.10 in the standard normal chart, you're going to get the number 0.9821. So remember, that's the area to the left of that z-score. So that's the unshaded area here. The shaded region in the right tail would be 1 minus 0.9821, and that's 0.0179. Well, we compare that p-value to the alpha value. The p-value in this case is greater than the alpha value. 0.0179 is greater than 0.0100. Therefore, our conclusion is do not reject the null hypothesis. Okay, in other words, the probability of getting this kind of sample mean, when I say this kind of sample mean, it means 24.7 or one that's even further to the right. Okay, the probability of getting this kind of sample mean is high enough that we say, you know what, it's reasonable that it came from this distribution centered at 24. Okay, it would be too risky for us to reject the null hypothesis. Okay, there's basically a 1.79% chance that we could get this kind of sample mean from a distribution centered at 24. We're only willing to take a 1% chance of rejecting the null hypothesis by mistake, so it's too risky for us in this case. Now, if the alpha value were 5%, if we were willing to take a little bit more risk, then we would come to a different conclusion, which is to reject the null hypothesis. In fact, when most people do research today, they're going to use the p-value method, and they're just going to report the p-value out and let people make their own decisions. So of the two methods, it's the p-value method that's probably used more often, and it's because you can just report the p-value out and let people make their own decisions based on how much risk they want to take. Now let me show you a two-tailed test before we finish up here. This one says the Weather Channel reports the average wind speed in Baltimore will be 8.0 miles per hour today. You think they're wrong. You record 32 random wind readings. Their average is 8.2 miles an hour. Population standard deviation is 0.6 miles per hour. Alpha is 0.05, that's 5%. Can you say that the Weather Channel appears to be wrong? Well, if you think they're wrong, that means you think that the average is not 8.0. Now, there's nothing about the word wrong that suggests that you think it's higher or lower, so you're going to use your not equal to sign here. So the alternative is that the average is not equal to 8.0. The null is that the average equals 8.0. When you did the experiment in research, your sample size was 32 and your sample average was 8.2, and you found out the population standard deviation is 0.6. Okay, now to analyze the data here, again, the sample size we chose was 32, so that's high enough to say that the sample mean comes from a normal distribution, so draw your bell curve. Assume the null hypothesis is true, so put 8.0 in the middle. And then we have the sample average 8.2. Now, when you're doing a two-tailed test, the sample average will fall on one side of the distribution or the other. Just shade in that tail. So 8.2 is in the right tail, so I shaded in the right tail. Now the p-value is going to be 2 times the amount of area that we shaded. Whenever you do a two-tailed test, the p-value will be 2 times the area that you've shaded. Okay. Technically speaking, it's this area plus an equivalent area on the other side. Okay. Remember, two-tailed test is kind of looking both ways. So when we say what's the probability that you get this kind of sample mean from a distribution centered at 8.0, well, this kind in a two-tailed test means one that is this far above or this far below. So you get 2 areas, one on each side of the distribution, but because they're the same sized area, you can just find the area of one and then double it. So in this case, we have to convert to z-scores in order to find that area. So take the 8.2 minus 8.0. Okay, so that's sample mean minus what you assume to be the population mean, divided by the population standard deviation, 0.6, over the square root of the sample size, which is 32. That works out to be 1.89. Now we've shaded the area to the right of 1.89. When we look up 1.89 in the table, okay, I'm not going to flip back and forth like I said, but if you do that, you can check the table. You'll get the number 0.9706, which is the area to the left of 1.89. So that's the unshaded area. That means that the area that I've shaded is 1 minus 0.9706. But this is a two-tailed test, so I'm going to have to double that. So that's where the 2 times comes in front of the parentheses there. Okay, so I subtract and then multiply by 2, and that gives me 0.0588. So I compare the p-value to the alpha value. P is greater than alpha by a little bit. 0.0588 is greater than 0.0500. So it's too risky to reject the null hypothesis. So my conclusion is do not reject the null hypothesis. Okay, that's the p-value method. There's a lot of similarities to the traditional method. In both methods, you're going to state the hypotheses, you're going to do the research and try to get your sample size, sample mean, and population standard deviation. You're going to end up converting the sample mean into a z-score. The only difference between the two methods is you compare the z-score to a critical value, that's the traditional method, or do you compare a p-value to the alpha value? That's the p-value method. Either way, you'll get the same conclusion.